Good day to all. This is the second part of our discussions for time value of money and starting with present value of cash flow streams. Last time we've had future value of the cash flow streams and we've discussed like for present value also that there are so-called mixed streams wherein the cash flow streams are not equal or not the same as opposed to the installments or annuities or the so-called series of payments of equal amounts. Then again, if equal amounts, these are called annuities. In addition, we have to know the term perpetuities, which are cash flow streams that continue forever. And for that, for perpetuities, the present value is the summation or the sum of all cash flows at time or specific time equal to 1 multiplied by 1 all over the quantity 1 plus r to the power of t or the time. Well, for the respective ordinary annuity, it would be more or less similar to what we've known. And then for other items like mixed streams, so we just have to take note that we are going to compute the present value of each and then add all the present value streams for each period, and then that will be the present value, hence summation. But for ordinary annuity, we can do the shortcuts just like future value. It's because the amounts are equal anyway. And we all know that in mathematics, if we have common items or factors, then we can just consider that as one item multiplied by the sum of the other factors. All right, so that's mathematics. Anyway, so to continue, for present value of an ordinary annuity for 5 years at 5.5% interest, just like future value in the last session that we've had, that we can basically compute. So for time zero, how much is the value of $1,000 at the end of year one, considering 5.5% interest? So this would be the amount. If you can notice, it is lesser because of course this will earn given a certain year or period. In this case, 1 year, or for 2 years. So 2 years, much lesser. And as we go along the way, the greater the number of years, the lesser the present value becomes. So just for us to take note of this. And then if we get the sum of all, then we get the present value of this particular ordinary annuity. It's just a review, although we can notice that the formula is somehow different, but then we can manipulate this formula. I do understand that some books would be present value equals payment or PMT multiplied by the quantity on the numerator 1 minus 1, the quantity of force 1 plus I to the power of negative n all over I, or I, periodic interest rate or effective interest rate, or we can say periodic effective interest rate is R also here. So I repeat, the present value factor normally is in the numerator or on the numerator, that's 1 minus the quantity 1 plus I to the power of negative n all over I. So how do we get that? Or we can replace I with R. Well, if you can just perform mathematics, remember, we can multiply this and then numerator to numerator and denominator to denominator. And then after that, remember, if this is 1 minus 1 and then all over 1 plus r to the power of n, the quantity of force, remember, this is an exponent. And if we place this or the quantity in the numerator, that's going to be negative n. So this becomes 1 minus the quantity 1 plus r to the power of negative n, enclosed in parentheses. And then in that case, so this leaves over 1, and r times 1, that becomes r. So indeed, 1 minus the quantity 1 plus r to the power of negative n all over r. All right? And that would be equivalent to this particular amount here. Okay. Next, what about for present value of an annuity due? For an annuity due, there is already an annuity or there is already a certain collected or paid amount at the beginning. And the present value, of course, if paid at time zero, equals to that amount. Remember, any item with exponent of zero equals 1. And any amount multiplied by 1 equals the number or the amount. So utilizing the formula, so we get this particular total amount. Although as a shortcut, we can do also this thing just like for future value. If for future value, we are going to consider if it is 5 years into 6 periods. So that's 1 plus I to the power of n is plus 1. So 5 becomes 6. Then minus 1 all over I or R. And then we are going to minus 1 on the total present value factor. Here it's different. For the number of periods, we are going to minus 1. So this becomes 4. But then on the present value factor, we are going to add 1. Why is that? Because of this particular amount. Remember, this is a time 0. So the present value is equal to 1. So we add 1 because remember, we deducted already 1 on the number of periods, therefore we add 1. But for future value, since we added 1 period, we have to minus 1 to the total present value factor. So you can, or future value factor rather. So that's respectively. So you can verify that by pausing this particular part here and compare with future value factors. So I repeat, for the future value factor, we are going to add 1 to the number of periods, but for the total future value factor, we minus 1. For present value factor, we are going to minus 1 on the n number of periods, but then we are going to add 1 to the present value factor. Okay, so what about for future and present values of a mixed stream, assuming 5 years and 4% interest? So you can notice that the amounts of the periodic payments are different with each other. Okay, so what we can do is that we compute differently the amount for future value and present value of each cash flow. So that's going to be FV of 1, which is the amount or the principal amount multiplied by or the cash flow or payment multiplied by the quantity 1 plus I or R to the power of N. Here it's different. It's the amount multiplied by the quantity 1 plus I or R to the power of negative N. So for future value that is compounding, this is a good point, but for present value factor, that's discounting. On another hand, what about for present value of a perpetuity? So this is going to be, or this is all about for a constant stream of cash flows that continues forever, as the term perpetuity or perpetual. So this is the formula. Present value is equal to payment multiplied by the summation or the total amount of the quantity 1 over 1 plus r to the power of t. This is when t is equal to 1. So in that case, this becomes 1 over r. And then after that, this means that payment is equal to r or the rate. Well, that seems automatic, but if t is equal to 1, ladies and gentlemen, so this leaves 1 over 1 plus r, right? And then if we do the exponential simplification, so that's 1 times 1 equals 1. R times 1 equals 1. So that leaves us like here as r, 1 over r. Okay? So I hope that is also clear. And payment is over r. So here's an example of a present value of a growing perpetuity, wherein aside from the rate, which is R, discount rate, there is a growth factor, and wherein the rate must be greater than the growth factor. So if this is the case for a growing perpetuity, the cash flow at period one is $1,000, and then the rate is 7% per year, and G is 2% per year. And so this is how we are going to obtain now the present value of that growing perpetuity. So $1,000 over 0.05, and that is equivalent to $20,000 then. In addition, what about if we do compounding more frequently than annually? In fact, I've already introduced this in part one, but just for us to be reminded that the R enclosed in this particular brackets actually would be the periodic effective interest rate. So if you say periodic, if R is annual as stated normally, but then it's going to be compounded semi-annually, the M becomes the number of compounding periods in a year. So if it is semi-annually, that's 2, quarterly, that's 4, and monthly, that's 12. Annually, of course, is 1. If that is the divisor or the denominator, then of course it's equal to the number. R over 1 equals R. And then M times N. So we multiply the number of years with the number of periods in a year. So that's M compounding periods. And this is for the continuous compounding, which is E, then to the exponent of R times N. So this is like a shortcut that we can use with scientific calculators for continuous compounding. So never ending compounding. And we have to take note as a whole that the more frequent the compound period, the larger the future value, of course. So the more the money earns interest in shorter periods of time, then the more the value becomes greater. And that is the future value when I said value. Okay, here's an example. So you can notice that by this particular amount, if it is just annually compounded or annual compounding, the value of the future value is lower than if semi-annual, but then it goes higher if we go to quarterly, and the more with monthly and bi-monthly or twice a month. So 24 periods in a year. And if we do continuous compounding, then the greater its value that is going to be. Now, we have to take note that in a contract, it's possible that there are going to be two rates. What is stated in the contract, which is also known as the coupon rate, or the stated rate, or the nominal rate, and the effective rate, or the yield of interest, or the market yield of interest. What is clear is that the stated is not necessarily equal to the effective annual rate. It's possible that the two would be equal and the effective could be higher than what is stated because of the charges and so on. So to get the effective annual rate, we have our formula here. So 1 plus r to the power of m, enclosed in parentheses to the power of m, and it's minus 1. So that's it for effective annual rate or effective rate or the market yield of interest if that is normal compounding. But if it is continuous, so we have here a formula E. E is a certain key in scientific calculators in which that's given to the power of R for the nominal rate and then minus 1. So here are our formulas then. Next, for annual percentage rate APR, then the stated annual rate is calculated by multiplying the periodic rate by the number of periods in 1 year, of course. The periodic rate, for example, that's monthly multiplied by 12, that's going to be the annual. And then the annual percentage yield is based on the effective interest rate, which is periodic, multiplied by the number of periods equal the annual percentage yield. And if I said number of periods, I'm talking about the number of periods in a year. We have to take note that in order for us to have more values in the future, then deposits needed to be accumulating the interest, or they have to stay put, and they have to, of course, stay there in certain deposits, or let's just say certain hands that we cannot just get them or withdraw them or get them for our personal consumption or use, so that such deposits would earn further interest or such amounts. Then we also have to take note of loan amortization. So we borrow money, and then normally what's stated interest rate is not the effective one. That's a realization that we obtained or we can obtain out of this one or this discussion, but still that's already discussed even in finance subjects, in investment subjects, and even in accounting subjects, especially with the amortization of the loan. Like, how do we compute such amortization? Then we also have the implied interest or growth rates, as said a while ago, with respect to perpetuity, in which that's the cash flow over R minus G. R is the nominal rate minus the growth rate. Then the number of compounding periods will have impact, of course, on our future value or even the present value. But compounding is more on the future value. So the more that the amount is going to be compounded in shorter period of time, the greater the future value. Then in real life, though, especially for financial management or finance, that involves finding the future and present values. And then time value of money, or TVM, is very important. It is because any analysis in financial management and any financial valuation techniques, and in fact, all of them, will be focused and essential to such. So TVM is very important because we start from here to be able to make very important decision making analysis. And this is the end of TVM, or time value of money. Thank you very much for listening. God bless us all.